So the example we always give students to picture an ionic compound is table salt, sodium chloride. So when sodium chloride forms, each of the purple sodium ions is surrounded by a chloride ion, which we can draw. You can draw it in several ways. You can draw it as a pair of ions like that. It's more accurate to represent it in a three-dimensional structure like this, where it's alternating positive and negative charges. And it looks like a cube. It's a cubic structure. And we usually represent it as lines that connect the ions. But keep in mind, the lines aren't really there. They just show the connectivity. Now, you might have noticed that sodium chloride crystals are cubic, and that's a consequence of the atomic structure on a microscopic level actually is cubic. So the macroscopic property of cubic crystals is actually a consequence of that. And so this is another way you'll see a crystal like sodium chloride represented, where the large blue spheres represent chloride ions, negative charges, and the small blue spheres represent the positive sodium ions. And it's in all three dimensions. And another way you could picture that would be a little bit more detail like this. Now notice that in this structure, the chloride is the yellow and the sodium is the purple. And appreciate the fact that the chloride ion is slightly larger than the sodium ion. And the main reason is because chloride has gained one electron, so it's slightly larger. Electrons are added to orbits around the nucleus, so therefore the electron that's added to chlorine makes the chloride ion a little bit bigger. And then the sodium ion, since it lost one electron and gave it to the yellow chloride ion, the sodium ion has shrunk a little bit from its parent sodium atom. And so they're usually represented as a slightly smaller ion in these sorts of pictures. And also appreciate the fact that if you look carefully, the yellow chloride ion is surrounded by 6 purple sodium ions. If you count 1, 2, 3, 4, 5, 6. And there are 6 yellow spheres around each sodium. Now it's hard to see that in here, but this one, look at this one. You see 1, 2, 3, 4, 1 in here, 5, and then there's one over here that's not drawn because we haven't drawn the next cube. Just remember, this is just a piece of a overall sodium chloride cubic structure. And on a macroscopic level, this would just appear as a white solid, but it's very soluble in water. Because of its high solubility and the fact that these sodium ions and chloride ions are held together by positive and negative charges, which is just the elementary physical static electricity phenomenon, it's a very strong interaction. So ionic compounds have very high melting and boiling points. It takes a lot of energy to strip the sodium and chloride ions apart. They're very stable. The melting point of sodium chloride is above 500 degrees. So another property of ionic compounds generally is that they dissolve very well in water. So this picture here is just showing you that when you throw a solid sodium chloride into water, what happens is the water molecules, these little molecules here, are attracted to the sodium chloride because water molecules have are what are called they're polar, which means they have an attraction for positive and negative charges. So the water molecules will come in and bounce off the sodium chloride crystal and actually pull off chloride ions and surround them. And they'll pull off sodium ions and surround them. And that process is called solvation, S-O-L-V-A-T-I-O-N. And it's the process of something dissolving in water. We sometimes call it hydration, for specifically meaning water as the solvent. So we're going to talk about this phenomenon a lot in this class, especially when we talk about solutions and how they form. But not all ionic compounds will dissolve in water really well. Some don't dissolve very well. And this is from another textbook, so ignore the 4.3, but when sodium chloride forms, I might have shown you in another video, but it's a very violent reaction. Elemental sodium, it looks like a silverish metal. It's very unstable and has to be kept under mineral oil because it will react with the air. If you threw a chunk of sodium into water, it would explode. It gives up its electrons so easily. You combine it with chlorine gas, which is just a greenish gas. You might have smelled smelled chlorine gas if you're ever in a swimming pool. That smell that you smell when you go to a hotel swimming pool, that is partly chlorine gas. Very low levels of it, but it has kind of a greenish yellowish color, and it's very toxic. So it is interesting to realize that two very toxic elements combine into a relatively non-toxic, stable compound that we use in food. It's a very violent exothermic reaction, so it actually starts on fire. What's burning is the gas chlorine, and so it gives off a lot of energy, which means that excess energy is lost, and therefore sodium chloride is very stable relative to the elements, sodium and chlorine. You can look at this up on YouTube. There's many videos. It's kind of fun to watch these. There's also a cool video. I don't think I showed you that, but if you look up the reaction between aluminum foil and elemental bromine, which is a very similar reaction, it also has similar characteristics of being very exothermic and giving off a lot of energy. Now, the other way you can use your table is at the position of the elements will tell you the ionic charges that are common. So here are some of the common ions formed by the main group and some of the transition elements. So go back to our periodic table briefly. So again, what you can keep in mind is that the main group elements, again, these two columns and these 6 columns over here, will generally form ions that have a +1, +2, +3, positive or -4, -3, -2, -1 ionic charge. Those don't form ionic compounds. And that's summarized here for some of the more common elements. Hydrogen, lithium, sodium, the alkali metals and hydrogen generally form +1 charges because they lose their outer electron. Beryllium, magnesium, calcium, and strontium will generally lose 2. And then aluminum, the only metal over here in the 3rd column that's of any importance to us, will almost always form a +3. And then you get into the, we're going to ignore the semi-metals, and then you get over into the non-metals. Oxygen is a common element found in ionic compounds. Notice it's 2 columns away from the noble gases, so it generally forms a -2. Sulfur is right below it, so it'll also form -2 ions. Selenium is also in the same column, -2. The halogens almost always form a -1 charge. So again, that's the nice thing about the periodic table. Any element that's in the same column as another element, they all form the same ionic charge. The transition elements, you can see going across from left to right, there is no trend. These generally are +3, +4, then it's +2. Chromium can be +2, +3, magnesium +2. There's no pattern. Look for patterns in the table. There's no pattern here. What you should appreciate about the transition metals is the fact that they can form more than one possible ionic charge. So transition metals form a lot more types of ionic compounds than the main group of metals do, the first 2 columns. So I do want to make a few more comments about this chart I showed you earlier in the video. I didn't draw it in, but nitrogen, the next column over from oxygen, in column, what you might be calling column 15 or column 5A, nitrogen atoms can take part in ionic compounds. They form usually a -3 charge because they're in this column right next to oxygen. You'll see a pattern. And phosphorus atoms will form a -3 charge. So you'll see -1, -2, -3, and then over here +1, +2, and then we can't predict transition elements. But why are they doing those specific? Why are they forming those specific charges? The simplest reason I can give you is they all want to acquire what's called a filled shell around their nucleus. So they all want to acquire the same configuration of electrons as the nearest noble gas, which is over here in column 8A, or sometimes called column 18. Noble gases, we know, are very stable. So we assumed that all elements, when they gain or lose electrons, are going to want a filled shell of electrons. So these only have to move one more over to the, you count the number of boxes you have to get. How do you get to the noble gas column? You count. I have to move one to the right here, so they gain 1 electron. I have to move these elements 2 to the right to get to the noble gases, so they acquire a -2 charge. I have to move 3 to the right to have these become quote-unquote like a noble gas. They acquire a filled shell. These over here on the left side of the periodic table have to lose electrons. Now, instead of gaining, for instance, this column here, instead of gaining 1, we skip the transition metals when we count electrons being gained or lost. So they have to gain 1, 2, 3, 4, 5, 6. That's very hard to gain 6 electrons. It's highly unlikely or impossible. So it's easier for them over here and the transition metals to lose their electrons. So they move to the left. So beryllium would lose 1, 2 to become like the noble gas. In this case, it would be helium. Magnesium would move 2 to the left and therefore lose 2 electrons and become like the noble gas above it to the right, neon. And sodium and lithium and potassium and hydrogen will lose 1 electron to become like the nearest noble gas. Now, hydrogen is unique. If it loses a proton, it's just a bare proton. But so it behaves, it's very easy to understand the behavior of hydrogen. But the other elements that are lower in the table, you have to just keep in mind that that's really what they're doing. They're just trying to get to a stable filled shell. And so when we write formulas, it's important to remember that when you see formulas like sodium chloride, magnesium chloride, calcium oxide, aluminum oxide, these are, in a sense, empirical formulas. They're the simplest whole number ratio of the metal and the nonmetal. But there's no such thing as a sodium chloride molecule or an aluminum oxide molecule. These just are the relative numbers of atoms. There is such a thing as a water molecule and a CO2 molecule, but those are covalent compounds. So when we talk about ionic compounds, which we're discussing here, metals and nonmetals, they form compounds like I showed you earlier. They have this sort of crystalline structure. It's not really a molecule. It's just a collection of positive and negative charges held together by electrostatic attraction. And they may or may not be soluble in water. So that's really what these subscripts mean. They're only telling you the relative number of atoms in the ionic compound formula. And there's a very nice trick you can use to write the formula. You just take the ionic charge of the metal and put it as the subscript of the nonmetal. And then you take the charge of the nonmetal and make it the subscript of the metal. And you've written almost always a correct formula of an ionic compound. And you can do that for most ionic compounds. So let's talk about some more examples. Let me change color here. Let's talk about the formulas of ionic compounds, how you recognize them, and how you write them. So the chemical formula is going to show you the simplest ratio. And so if you take, for instance, you have magnesium and phosphate. Now, I haven't discussed these yet. This is called a polyatomic ion. It's just a group of atoms that work together as one unit. They behave exactly like a chlorine atom would in an ionic compound, or a bromine atom, or even a nitrogen atom. So as I discussed or just showed you a few minutes ago, these generally acquire -1. These will be -3. And this polyatomic charge just happens to form a -3 charge. So how would you write the ionic formula that would form between magnesium and what we call phosphate ion? Well, magnesium is in the second column of the periodic table, so it's going to generally lose 2 electrons. So you'd write 2+, and then all you have to do is crisscross the charges. You take this charge and write it as a subscript over here, and you take this charge and write it as a subscript over there, and you ignore the positive and negative. We're just talking about relative numbers of elements and or polyatomic ions. So you'd write the ionic formula you would form would be Mg subscript 3 and phosphate subscript 2. But very important to remember that if you have more than one polyatomic ion, you have to put it in parentheses and write a 2 like that. Now, if I didn't do that, that's the correct formula. That's a compound called magnesium phosphate. If you didn't do that, it would look like this, Mg subscript 2 PO42. That would be 42 oxygen atoms and not 2 phosphate groups. That's wrong. So you have to put those parentheses around the polyatomic group. Again, now I'm going to talk about this more as we go along here. A polyatomic ion, just to clarify, is a group of atoms, so it would look something like this. Don't worry, I'm not expecting you at this point to draw these, but it moves as a unit. So it kind of looks like this, and it just has a -3 charge. At this point, we're not going to worry where that charge is, but it moves as a group. It works as a group. These never leave each other, and it behaves just like these. It's just a group of atoms that carry some charge. Some polyatomics, there's only 1 or 2 that have more than 1 atom in them. There's only a couple that are positively charged. The vast majority contain oxygen and some nonmetal and have a negative charge. So that's why it's very important that you put the parentheses around that. So once you know the numbers and kinds of ions in a compound, it's pretty easy to write the formula. So let's just clarify again. So we're talking about formulas of ionic compounds. You list the cation first, so it's always cation plus anion, A-N-I-O-N. Now, I don't think I've commented on what a cation is or clarified. That's just a positive charge, and anion is a negative charge. So we write NaCl and not ClNa. It's always the metal first. You'll notice it's almost always I don't even know if there's exceptions to this. It's almost always the element further left that's written first, followed by the element that's further right written second. And that will also apply to covalent compounds that consist solely of nonmetals. Make sure that you eliminate any common factors from the subscript. So if you use that little trick I just showed you, let's say we have a magnesium ion and an oxide ion, and we're going to write the formula using that little crisscross trick to write the formula. You would write Mg2 subscript 2 oxygen subscript 2. However, that would be wrong because you want to reduce it to the simplest whole number ratio, kind of like you're reducing a fraction 6/8 to 3/4, or 5/10 you would reduce to 1/2. You would just divide both by 2 and write it as MgO. That is the correct formula for magnesium oxide. The other thing you got to remember is you do not write the charges of the ions. So for instance, if you have potassium fluoride, that's the correct way of writing it. You wouldn't write K positive F minus. I see this a lot from students. Do not write the charges in the formula. So for this one, you'll often see students do this, and maybe it's because they're kind of just keeping track of the charges. But if you were going to tell me or write the formula for magnesium oxide, you'd write this. You wouldn't write that. And again, as I already said, you would use parentheses around a polyatomic ion. So the formula for aluminum sulfate is Al2 and 3 SO4 groups. So you'd write the SO4 group in parentheses and like that. So that's going to take a little practice for you to recognize a polyatomic ion and write them correctly. Now there is a sheet, I don't know if I have it on Canvas, but I may give this to you in discussion. I just have a grid. You can find these online as well. Lots of teachers use them. But just giving you some practice for writing formulas. We will write the positive charges over here and the negative charges over here, and then give you some practice writing the formulas using this this technique I'm showing you here. I'll either put that online or I might use it in discussion sometime. Now that you know a little bit about how to write an ionic formula, let's talk about how to name these. You've heard me mentioning names of ionic compounds in this video. Naming compounds. Now we're going to talk about ionic right now. So how do you name them? They're named by citing the cation first. You say cation first, and you'll usually have a space and then the anion name, but you'll change the ending of that name. Or you'll say the name of the cation first, and then the polyatomic ion will be stated second, like that. That's pretty much covers all ionic compounds. Now, some metals will form more than one ion. The transition metals form more than one ion, so we have to come up with another rule to clarify those as well. You need to specify the charges. So let's just give you some examples again. So if you look back, I wrote some formulas. Let's see, I wrote MgO. So that's named the cation. Now you don't change the name of the metal. You just write it. It's magnesium ion. It's really made up of magnesium +2 and oxide -2. This is a magnesium atom written. If I see Mg, I just call it a magnesium atom. If I see Mg+2, it's a magnesium ion. But I don't write the word ion when I'm naming a compound, so I just call it magnesium. Let me rewrite that here. And then the second element, oxygen in this case, is a -2. I change the ending. It's oxygen, but I drop the ending and I add IDE. So this would be magnesium oxide. It's not, now that's a little, you won't always just drop the last letters and add IDE. Sometimes you will have to drop or keep a few of the letters. And you'll see what I mean when we go through some more examples. So nitrogen becomes nitride, so that would be N-3. Sulfide is S2 negative. All the halogens, like when you see Br negative, that's the word bromine with the ending just changed to IDE, bromide. So you see they all end in IDE. And that only goes, that IDE rule only applies to what are called monatomic ions. When I say a monatomic ion, I mean one ion by itself. When I say polyatomic ion, I mean a group of atoms that move together that carry some negative charge. So again, this is a series of rules that I'm giving you, and you'll have to practice. So these compounds that I've been drawing, you could call them binary compounds. They're made up of two or more elements, or they're just made up of two elements. Sodium chloride, 2 elements. MgO, 2 elements. Calcium sulfide, 2 elements. Those are binary. Compounds like when sodium would combine with phosphate would be Na3PO4. That is not a binary compound because it contains more than 2 elements, but they're all ionic compounds. But the rule for naming a compound that contains a polyatomic is slightly different than a binary compound. This is just change the element, the second nonmetal to an IDE suffix. Chlorine becomes chloride, oxygen becomes oxide, sulfur becomes sulfide. But let's name a few with polyatomics. Na3PO4 would be sodium phosphate. The name of this ionic the name of this polyatomic is the phosphate ion. We don't change the ending of the polyatomic when it's in a ionic compound. We just state sodium phosphate. And we don't call it sodium ion phosphate, we just call it sodium phosphate. And then another clarification, again, is when you have a transition metal, how do you distinguish those from other ionic compounds? Transition metal ionic compounds, I'll call it. I'm trying to write kind of quickly in these videos, so I'm hoping I think my writing is neat enough for this point, for this purpose. Let's say you had the compound CuS. How would you name that? Well, according to the rules I've discussed so far, you might say it's copper, and then it's sulfur, but it's a binary ionic compound, so you just change the ending to sulfide. That isn't good enough because copper can form a compound that looks like this. That's also a binary compound, ionic compound, because it contains just two different elements, but it's clearly different. So we can't call that copper sulfide too. Each compound has a unique name that no other compound has. So we have to add something to the name of these to clarify that. So what do? You use Roman numerals. So what would the Roman numeral be for that compound? Easy to figure out. You just say, to ask yourself, okay, if copper is with one sulfur, I'll draw it here, what would the charge have to be? Well, I know from the position of sulfur in the table that it's in this column here. So sulfur needs to gain 2 electrons to have a filled shell. Therefore, it's going to have a -2 charge. And copper, if it's written like this, must be an equal and opposite charge, because all ionic compounds have a 0 net charge. That's another thing I haven't mentioned. This is critical. The sum of the ionic charges always adds up to 0 in an ionic compound. It always adds to 0. Because ionic compounds do not have a net charge, they only have charges within them that balance each other. So this would be the ionic charges of the copper in this formula and the sulfur in this compound. Compare that to this compound here, Cu subscript 2s. That would be 2 coppers. That would represent 2 coppers and 1 sulfur. Well, the ionic charge of sulfur isn't going to change because it's a main group element. But this, as I said before, the elements in this part of the table can have more than one possible positive charge. That's why they're put in this special section of transition metals. So copper, if you're going to have a 0 net charge, must have a +1 charge. So you don't have to put the 1 plus. It's implied that it's +1. And you can see that this is a total of +2. This is -2. If you add them up, you always get 0. And that goes for any ionic compound. How would you name, let's say, something like compound that has this formula? Lead PbCO3. What would the name of this be? Well, it would be the name of the element. I think I jumped a little ahead. Yes, I actually jumped ahead of myself. Let me go back here. I didn't clarify the names of those. Sorry about that. So how do we distinguish the name of those two compounds? Well, all you'd have to do is say, okay, they're both copper sulfide, and leave a little space there. That one's copper sulfide, this one's copper sulfide. But all you have to do to distinguish the two is add a Roman numeral. So this is copper with a +2 charge, so that would be copper with a Roman numeral 2. And we usually write no space in between the R and the Roman numeral, but we would put a space here. This compound here would be copper 1 sulfide because it's made of copper ions that have a +1 charge, and there's 2 of them to balance out the 1 -2 charge. And let me rewrite those properly here. So just so we have, you develop good habits. It's copper, no space, parentheses with a Roman numeral 2, and then a space, and then the word sulfide. And then this one, the other one would be written copper, no space, Roman numeral 1, then a space, then the word sulfide.